we're going to be solving a whole bunch of different types of trig limits in this particular podcast. And we're going to start off with a nice easy one. Sometimes you can substitute it to find the limit. So don't make something more complicated if it's not more complicated than it needs to be. So cosine is defined when x is 0, right? And the 0 up in the numerator there is no problem, right? It's a 0 in a denominator that's going to be a problem. But cosine evaluated at 0 isn't going to be 0. So sometimes you can substitute to find the limit. Sometimes f of c equals the limit as x approaches c. So here, nice, easy, no concerns. We'll just substitute in. So we have 4 times 0 divided by cosine of 4 times 0. This is going to be 0 in the numerator. You've got cosine 0 in the denominator, and the cosine of a 0 degree angle, that's 1. And so our limit is 0. Right? So no big stress on this one. Let's look at another problem. All right, so now we're going to find the limit as x approaches 0 of 1 minus cosine x over x squared. Now this one, you can't just plug 0 in. You will have, as the numerator is going to go to 0, that's real clear. And if you were to do substitution, numerator goes to 0 because that's 0 squared. Denominator goes to 0 because that's 0 squared. Numerator goes to 0 because you're going to have 1 minus cosine 0, and cosine 0 is 1. So you have 1 minus 1. And that's 0. Right? So obviously this is going to not be one for substitution. Right? So we'll try something different. So use trig identities in algebra to find the limit. Right? So if you can't substitute, if it's not that sign rule, try Pythagorean identity. Right? We don't have anything up there right now that could be a Pythagorean identity, but if we multiply by the conjugate, we will. So if you have a binomial as part of your, as one part of a fraction, so you have a fraction, you have a rational function, and one part's a binomial, try multiplying by the conjugate. Not going to work every single time, but a lot of times it will. And with cosine, it's going to give you something that you could substitute using a Pythagorean identity. All right, so multiplying by the conjugate helps us use Pythagorean identity. All right, so sine squared x plus cosine squared x equals 1 if you subtract cosine squared x from both sides. 1 minus cosine squared x, if we see that, we could replace it with sine squared x. And then we can use the sine rule. All right? So now let's take a look. All right, so we're going to multiply by the conjugate. We have the limit. Remember, do not drop this limit statement until you're going to substitute. So long as you're doing algebraic manipulation, leave the limit in, right? Because it's not the value of the function. If we have an indeterminate limit, the value of the function is not defined for that value, right? But the limit is. So now we're going to multiply, right? So we'd have 1 times 1. That's going to give us 1. Those middle terms will drop out because you'll have cosine x and you'll have minus cosine x. And then we have negative cosine x times cosine x. So that's going to be negative cosine squared x. Remember, that means that all of cosine x all squared. In the denominator, don't distribute. Just leave it like this. Right? We know the numerator, we're headed towards something. We're headed towards using the Pythagorean identity. That's the whole reason we multiply by the conjugate. The denominator, there's no reason to distribute. Let's just leave it like that. Maybe there's something we can cancel out, right? We can do something better with it, right? There's no canceling right now. If you were to factor 1 minus cosine squared x and factor out the 1 plus cosine x, you'd be right back to where you started with. So that certainly wouldn't be our goal. But we definitely don't want to necessarily distribute. That's just extra work. We can evaluate it like this, and let's see where everything else goes. All right, so now we have the limit as x goes to 0. Let's replace the 1 minus cosine squared x with the sine squared x. Now we can use our sine rule. And just a little reminder there, remember sine squared x means sine x all squared. The same thing with cosine squared x. it means cosine x all squared. We just put the square in between there as just a notation. All right, so we have sine, and sine, we know we have a special rule there we can apply thanks to the sandwich theorem, and that's easy to work with. And now you can see why I said don't distribute, right? Because I need the sine squared x and the x squared together, right? I need those together to be able to use the sine rule. We're going to split this fraction. Right, so I'll even write that in here. We're going to split the fraction. So you should write that too, so you remember. Right, I can rewrite this as two fractions, as a product of two fractions. I want the sine squared x and the x squared to go together. Now I can use the sine rule here. We'll just call it the sine rule, and that's where when we have the limit as x is approaching 0, of a sine something over the same something that we're taking the sine of, we know that that limit's going to go to 1. Now we just need to rewrite the other part of it. We have nothing left in the numerator on the for a fraction, so that means there's 1, right? Sine squared x times 1. The x squared is going with the sine squared x, and the 1 plus cosine x is going here. Right? We have all we've done is rewrite it. It's still the same, just looks a little different, but is the exact same value. So now we can take the limit as x approaches, actually I don't need to write that again. You know why I don't need to write it again? Because now we're going to substitute. Right? Now we can do some substituting. This part here, oops, I forget, if I erase, my color goes back to what it was. There we go. That part there, that's just going to equal 1. Right, because it matches. We can plug into the other part I've got, because it's not going to be indeterminate, or it's not going to be 0 over 0, right? It's not going to be indeterminate because I've got a 1 in the numerator, right? We're not saying it can't be undefined. It's not. But it certainly can't be indeterminate, right? So we have 1 over 1 plus cosine 0. Well, cosine 0 is 1. So we've got 1 times 1 plus 1 in the denominator there. Makes that's a half, which means our limit is a half. And there we go. Right? So we're going to be using all kinds of properties from our trig functions. Right? So you see a difference there or a sum, you be thinking, maybe I should multiply by the conjugate. Especially if that something is cosine. Right? Because that's going to give us we're going to be able to replace it with a sine, because we'll have a so if you've got something that looks like this, we might be able to replace it with a sine, and then we're going to be able to use the sine rule. Is that going to work every single time? No, but it's a starting point, and it worked here. It all depends what the rest of the function looks like. So we're going to try all different things when we're solving these. We want to find the limit of tangent x over x as x approaches 0. Well, direct substitution is going to be a problem, right? Because tangent of 0, well, that's 0, right? Because tangent is sine over cosine. Sine is 0 when x is 0, so is tangent. And then, of course, you plug in 0 for the x, and that's 0. So direct substitution yields the indeterminate form, 0 over 0. Right? So we want to solve this problem, we're going to rewrite it as tangent x as sine x over cosine x, and then we can do something much better. We could use the sine rule. So we have the limit as x approaches 0. So whenever you can rewrite it in terms of sine. If your limit is going to 0, it's a good thing. So we have sine x over cosine x all divided by x. Let's rewrite that. All right, so we have the limit as x approaches 0. And we have sine x over cosine x. I can rewrite that as times 1 over x. I need the sine x and the x to go together to be able to use that sine rule. All right, so we want these two to go together. All right, so we're going to put these ones together because we can use then the sine rule. They'll match. And our limit's going to 0, and that's what we needed. All right, so I'm just rewriting. I have the limit as x half my m is missing. Limit as x approaches 0. Now we have the sine x over the x times 1 over cosine x. Have we changed our expression in any way? Other than the look of it, we have not changed anything. We still have sine x times 1 in the numerator. We still have x times cosine x in the denominator. The order you multiply in doesn't matter whatsoever, right? Multiplication is commutative. Now we can use the sine rule, right? So now I'm going to get rid of the limit because we're substituting, or we're using the property. So the limit for sine x over x, that's going to be 1, and I think you should write that in to kind of show what that is. And then now we're going to substitute in for cosine. So now we have 1 over cosine 0. Well, cosine 0 is 1, so you've got 1 times 1, which is 1. And there we go. Easy cheesy, lemon squeezy with a little substitution. All right, so important things to remember. The tangent is sine x over cosine x, and Pythagorean identities. So here is the graph of f of x equals tangent x over x, and look at that, it does appear that our limit is approaching, as x approaches 0, from the left-hand side and from the right-hand side is approaching 1. There is a hole there in the graph, you cannot, so f of 0 does not exist, that's undefined. However, the limit of our function here, as x approaches 0, that's equal to 1. And we show that on the other page. All right, so let's do some more with tangent. Now that we have the hang of this, all right, let's rewrite it. So we have the limit as x approaches 0. I'm just going to rewrite it. So I've got sine x over cosine x divided by 3x. Let's split it. We got the limit as x approaches 0, sine x over cosine x times 1 over 3x. These have to go together, the sine x and the 3x. So the limit as x approaches 0 of sine x over 3x times 1 over 3x. Oh, excuse me, 1 over cosine x. But we have a problem. Our x's don't match, right? We have a 3x in the denominator, and that's sine x. You can't do anything to sine, but you could do something to the 3x. So we have the limit as x approaches 0 of sine x over 3x times 1/3. Now that's going to make that be an x. But you can't just go willy-nilly multiplying by 1/3. So if we multiply by 1/3 in the denominator, I have to multiply by 1/3 in the numerator. You can either stick it over here. If this makes more sense for you to put it over here, or you can put it over here. It doesn't make any difference. That's still going to be a third either way, whether I write it like that or I write it like that. But if that makes more sense to you because you can see it in the numerator and you can see it in the denominator, either way it's going to be a third. All right, now things are looking up for us because we're almost done. So we have, oops. So that's all easy stuff right now. It's a little rewriting, a little multiplying. The limit as x goes to 0. We have 1/3 sine x, right? And I'm actually going to put that 1/3 all by its little lonesome there. I'm going to try and shove it in a fraction. Let's just put 1/3 there. Then we have our sine x over x. And we can just put some parentheses in here to our multiplication. And then times, whoops, we lost a x on our cosine. Can't take the cosine of nothing. 1 over cosine x. Now we can just substitute in, right? And if I just wrote a little bit smaller, I'd have plenty of space. We'll just move everybody up. There's all that space up there, and then I have plenty of space. All right. We have 1/3 sine x over x. That's just going to be 1. And then we have 1 over cosine 0. Make sure you're showing your substitution, even though it's just 1. So 1/3 times 1 times 1, that's 1/3. Right? I think we all got that cosine 0 is 1. Let's look at this one over here. I'm already going to just move it up. Very, very similar. All right, so now we have the limit as x goes to 0 of sine 3x over cosine 3x. Let's save a step. Instead of writing it as divided 3 over x in the bottom there, let's just make that times 1 over x. We know that's what it's going to look like. So let's save ourselves one step. All right, so now we're going to split. Right, so these have to go together, this and this, right? So we can use the sine rule. So we have the limit as x goes to 0, sine 3x over x times 1 over cosine 3x, right? Except we don't match. So we need to multiply the numerator and the denominator by 3. So we do match. And now all is good, right? And now we can just finish this problem off. See, I use a little less steps over here. We combined a couple of them. We did fine. The combinings there. So we're going to have this part over here. Actually, I'll write this one more time just to make sure it's clear. So we've got a 3 times a sine 3x over 3x times a 1 over cosine 3x. All right, so now we can find our limit because either we can substitute or replace. So the 3 is, of course, just going to stay the 3. And then the sine 3x over 3x, that limit is 1. And then now we have 1 over cosine times 3 times 0. And of course, that's going to be 0, which means that's going to be 1. We've got 3 times 1, which is 3. Oh, look how easy this is. Easy, cheesy, lemon squeezy. Once you get the hang of it. Maybe it doesn't seem easy when you're watching it now. I hope it does. All right, let's look at this one. So we have the limit as x approaches 0, sine squared x over x. Of course, we know that's going to be indeterminate. We tried to plug in. My x looks funny. It doesn't look any better. There we go. All right, so we're missing something here. We are missing an x in the denominator. We need an x down there. All right, so we have the limit as x approaches 0. We need sine squared x over x squared. All right, so now we've multiplied the denominator by an x, right? We have to multiply the numerator by an x. So now we have a times x. Now we can take our limit. This one was a short one. All right, we know that part's going to go to 1. And we can substitute in for the x. It's no problem now. And that does mean our limit is 0. All right, so here our limit was 0, thanks to that x, all right, but not indeterminate, because that x is in the numerator. Let's look at the next one. All right, so we have the limit as x goes to 0, tangent x, plus sine x, all over x. All right, so we need to split this particular fraction. Right? Right, we're gonna split it and rewrite it as 2 separate fractions. Right? So notice, so this is a sum, not a product. Be careful. Over here, when I had a product, all right, so here I have sine x over cosine x times 1 over 3x. I can rearrange the terms. I just need to make sure I've got a sine x in the numerator. I have to have a placeholder. I have to have the 1 in the numerator as well. And then I need to make sure cosine x and 3x are in the denominator. It doesn't matter who's where, right? Because it's just multiplication. Be careful. You can't just split this up. You can't say, okay, sine, you take the x, because it's a sum, all right? Both terms get the x because it is a sum, not a product. I'm just rewriting it. Sometimes we combine fractions, sometimes we separate them. For with only one thing in the denominator, there's no problem separating this. So we have the limit as x approaches 0 of tangent x over x plus sine x over x. Well, we know what sine x over x is. Do we know what tangent x over x is? Have we solved that one before? Let's find it. Not there. Right here, right? Tangent x over x, we know that limit is 1. Oops, it doesn't say limit right there. But over there it says limit, right? And over here, we solved it. So I am okay now for tangent x over x. Since we've just solved it, we know it's going to be a 1, right? So we can just add that a little bit to our notes over here. Let's write it next to it because we're recognizing that we've already done this problem, or this part of the problem. Come back. This part of the problem. So we know that, let's just put it over here somewhere, tangent x over x, that's not going to equal that, but the limit will. The limit as x goes to 0 of the tangent x over x, we already know that that's 1. So I'm fine. Let's find our limit, and it's just 1 plus 1, which is 2, right? Because each one of those is 1, right? The limit of tangent x over x as x goes to 0 is 1, and the limit of sine x, oops, he lost an x, sine x over x as x goes to 0 is also 1. All right, so you do have to split it, but once you realize that, you've split it, you realize, oh, these are just both 1. Look at that. But do make the split. All right, so now let's take a look at this one. We see a cosine, and we see a binomial in the numerator. So be thinking, multiply by the conjugate. So you can do an algebraic simplification with Pythagorean theorem, with Pythagorean identity. And you want to split the product, because you can use sine. Right, our special sine rule. Right, so we're going to take this and we're going to multiply. The limit as r goes to 0 of cosine r minus 1 over r squared. And you should just be thinking that as soon as you see this problem. Be thinking conjugate. I need the conjugate. Right, and this would be cosine r plus 1 over cosine r plus 1. We multiply that. Limit as r goes to 0. Right? And we have cosine r times cosine r is going to be cosine squared r. The middles will drop out, right, because you've got a positive cosine r and a negative cosine r. That's what's always going to happen when you multiply by the conjugate. But the last terms will be left negative 1 times 1, so that's going to be a negative 1. Don't take any time to distribute in the denominator. You're just going to have to undistribute. So I actually don't just ever distribute in the denominator. I always leave it in factored form. Either I can just plug into the factors, or I needed it in factored form anyway. So I never distribute in the denominator. All right, so now we're going to replace the cosine. So oops, we don't have 1 minus cosine squared r. We have cosine r minus 1. We're going to have to rewrite this first. So we have the limit as r goes to 0. Let's rewrite it. We have 1, negative 1, plus cosine squared r over the rest of that. So close. But it's not exactly 1 minus cosine squared r. But hey, if we just factor out a negative 1, it will be. All right, so we have the limit as r goes to 0. We'll pull out the negative 1. Now it's going to be 1 minus cosine squared r all over r squared cosine r plus 1. Now we can replace this with sine, that 1 minus, so this part right here. Boop. All right, that's going to become now sine squared r. We're going to split this product. So now we have the limit. Let's rewrite and kind of split at the same time, because we're going to run out of space. All right, so we've got, maybe I'll write it twice just to make sure. Negative, yeah, the negative there. And I'll just write them as negative 1. We have the sine squared r. And then we have r squared times cosine r plus 1. Now we're going to split it because it's a product. The sine squared r and the r squared go together. This is our last step before we substitute. The limit as r goes to 0. We've got negative, and actually we can put, let's just put the negative with the cosine. All right, because it's just negative 1 times. And let's just keep the sine together. So we have sine squared r over r squared. those go together, and then we're going to have times, and the negative 1 can go right there because the order we're multiplying in doesn't matter. And then in the denominator of that goes cosine r plus 1. So all we've done is we just split our little product into two little fractions, but it's all the same thing. If you were to multiply it back again, notice you have the same things you had before. The limit for sine squared r over r squared, that's going to be 1. And then we'll plug into the other part. So we have 1 times negative 1 over cosine 0 plus 1. Well, cosine 0 is 1, so now we have 1 times negative 1 over 1 plus 1, which is negative 1/2. And we're done. Right? So hopefully you're getting the hang of these, because there's only so many ways on some of these that we can solve them. Right? So when you see certain patterns, your head should be thinking certain things. Right, let's see where I am. I'm getting close to where I'm going to say, let's do this one. And let's save that one because it had a little problem. And let's do this one right now. All right, and this will be the last one for this podcast. So we want the limit as x goes to 0 of secant x minus 1 times x over secant over x, or x times secant x. All right, so check to see about the substitution. Clearly the denominator goes to 0. As soon as, because you're going to plug in 0 for x, it doesn't even matter what secant x is, right? You're multiplying it by 0, so it's 0. Up in the numerator, secant, come on, 0 minus 1. Secant is the inverse, I should say, excuse me, not inverse, reciprocal. Secant is the reciprocal of cosine. It is also 1 when x is 0. Right? Those are going to be equal, right? Because then, and so you have to write this down. But cosine, right, would be r over x, and secant is just, oops, excuse me. Ignore that. I had secant in my head first when I was going to write. Cosine is x over r. Secant is r over x. Right? So this x here, of course, is the adjacent. Right? So they use the same numbers. They're both 1s on the unit circle. So because that's a quad angle, and so they would just be 1. All right. So that means this is 1 minus 1, and that's 0. Right? So obviously substitution's not the thing we can use right here. And actually most of these in this lesson are not going to be using substitution. So we could try multiplying by the conjugate. It's worth a try when you have a plus or minus. If it gets worse, you can always scrap that plan and try a new plan, as you'll see in the next podcast. All right, so we have the limit as x goes to 0. We have secant x minus 1 over x secant x, and then we're multiplying by secant x plus 1, secant x plus 1. There we go. All right, in the numerator, we'll have the limit as x approaches 0, because we'll have a positive and a negative. Where's my secant? And then we'll have a minus 1. There we go. In the denominator, the last thing you want to do is distribute that. You're just making it much worse. All right, if we need to, we'll put things together and whatever, right? So just leave it like that, all right? There's no reason to necessarily multiply out in denominators. It's numerators so that we can split things up. And that'll hold for everything. I rarely multiply out in a denominator ever. All right, so secant squared x. I can never remember the Pythagorean identities, and I just don't think it's worth my brain power to use part of that, of my gray matter, to have something memorized. So I just bother to memorize sine squared x plus cosine squared x equals 1. That's an easy one. And then if you divide sine squared x, and as you divide everything by sine squared x, you get another Pythagorean identity. If you divide by cosine squared x, you get the other one. All right, so then I never have to bother to memorize, because if I'm just memorizing, there's a chance I could get a sign wrong. It's a plus or a minus. I don't have to worry about it. All right, I added the wrong two together. Just remember one, and then you can always derive them. It's so easy. All right, so if I divide everything by cosine squared x, I've got tangent squared x plus 1 equals secant squared x. Right? The whole goal here is to have something to replace the secant squared x minus 1 with. So that would be the one you'd want, the one that's going to give you a secant squared x. And if I divide by cosine, 1 over cosine squared x is going to give me the secant squared x. That's how you can decide. All right, so now that we've got a secant squared x, if we just subtract 1 from both sides, I'm looking over here at step number 2, we've got tangent squared x equals secant squared x minus 1. Let's get rid of secant squared x minus 1 and replace it with tangent squared x, a much friendlier function to work with. If you haven't realized, sine x and tangent x are much nicer to work with. All right, at least for these problems. So we're going to have the limit as x goes to 0. Now this is tangent squared x. And now I've got x secant x times secant x plus 1. Now we can replace that tangent squared x, right? We can replace that with use the quotient identity, replace it with a sine squared x and a cosine squared x. Right? Let's kind of rewrite this one. So we have the limit as x goes to 0. Let's replace the tangent squared x. We'll make him a sine squared x over a cosine squared x. So I'm going to probably be rewriting at this point just to save ourselves a little bit of space. There we go. And now the rest of this is just going to be 1 over everything else. Right? So we have x secant x plus 1. Now I've got a product. I can move things however I want. With the sine squared x, has got to go that x. And I need one more because I don't have enough x's. Right? We need 2x. We need x squared. So we have the limit as x goes to 0. Now that it's a product and no sum or difference, I can rewrite this however I want, so long as I've got everything is supposed to be in the numerator and everything is supposed to be in the denominator. So sine squared x, you're going to get not only an x, but an x squared. If I do that, I've got to have another x there, all right? So we got one more here. We multiplied by x there, right, because there already was one x. I need to multiply by one more x, all right? So all I've done is I've multiplied the numerator and denominator. I split this so the x could go with the sign, and I multiplied the denominator by x. I can do that so long as I multiply the numerator by x, and that's all I did there. All right, everybody who's left, you're going with x. So that means secant x. Does that not look like an 8? Secant x, and then we have a secant x plus 1. All right, so now things are looking good. We can now find our limit. Sine squared x, oops, we forgot somebody. And I have no idea how that happened. Just magically comes up all by itself. We forgot somebody. We forgot cosine squared x. I said as long as we have everybody represented, and there we go when we leave off cosine squared x. It's a good thing I took a last look just to make sure I had everybody. Now we have everybody. We've got sine squared x, and we multiplied by x in the numerator. We've got x squared now because we multiplied by x in the denominator. We got the cosine squared x, we got the secant x, we got the secant x plus 1. Oh, now it's good. All right, so the sine squared x over x squared, that's going to be 1. Now we'll just plug into everything else. So times, we've got a 0 in the numerator. So long as we don't end up with a 0 in the denominator, things are fine. So we have secant 0 times secant 0 plus 1, and then we have cosine 0. And I wish I'd written a little bit smaller, because I have only one little number to write at this point. Everything in that denominator is a 1. Secant 0, we already said, is 1. Secant 0 plus, well, actually, everything is a 1 except for one thing. Secant 0 plus 1, that's a 2. And then cosine 0, that's a 1. So we've got 1 times 0 over 1 times 2 times 1. But so long as it's not a 0 in the denominator, when it's not, doesn't really matter what it is because it's 0. That is our limit. I think I could have written this a whole lot prettier. Maybe before I post it, I'll write it a little bit nicer. I don't know why I leave all that space in the top there. Well, that's the last one I'm going to do in this podcast because that's enough. Right? So we'll look at the last few in the next podcast. Thanks for watching. And remember what we've learned here in this particular podcast, right? Multiplying by the conjugate is a good idea when you've got a plus or minus. Pythagorean identity is your friend. You can use a quotient identity for tangent to get a sign in there, and you can do whatever you want to the numerator to make, or denominator to make it match your sign. Just do the same thing on the other side of the fraction. Thanks for watching. Bye for now.